So hello everyone, this is Lin Yansu from UCLA. So I'm going to talk about a paper model-based reinforcement learning with a generative model is Minimax optimal. Okay, so this work is joint work with Alekh Agarwal from Microsoft Research, Sham Kakade from Microsoft Research and the University of Washington. All right. So this talk is about the very basic reinforcement learning model, the discounted Markov decision process. So in this paper, we can see the simplified setting, although it is still very general. That is, the reward function is bounded in between 0 and 1. Okay. So as usual, we have a set of states, a finite, and a set of actions, also finite, attached to every state action pair. So once an action is taken at a state, and the agent is going to receive a scalar reward R, and the system is also have a transition to another state S prime, based on some probability P as A S prime, which is fixed but is unknown. Okay. So the reward and the agent counts the reward based on discount factor that is a number very close to 1. So of course, our goal is to try to find a good policy that is a function mapping states to actions. Okay. So the value function is defined as usual. You just play according to the policy, and then the expected non-term discounted reward is the value function of the policy. And our goal is to find a near optimal policy. That is, the value function of the policy is at most epsilon away from the optimal value function. Okay. So of course, if the model is known, for instance, you know the probability transition, you know the reward, you know everything, right? So then, this policy can be obtained via the dynamic programming method like value iteration or policy iteration. So unfortunately, in the learning setting, you don't have this model in the memory, so you cannot solve this via dynamic programming. So in order to, so our question becomes how many samples you need in order to get a good policy, right? So in order to answer this question, we consider the very basic setting that's called the generative model first proposed by Kearns and Singh. So this generative model basically get rid of exploration as a lot of subtlety for the exploration, right? So this generative model considers the setting that the agent can obtain samples from any state action pair, and then we can use those samples to compute a good policy. Okay. So basically, for this particular setting, there are already a lot of existing results and bounds. For instance, Azada 2013 gives an information theoretical lower bound saying that no matter what algorithm you're using, the number of samples to get an epsilon optimal policy with constant probability required is proportional to number of states, number of actions, and then 1 over 1 minus gamma to the minus 3. So remember that gamma is a number very close to 1, so 1 over 1 minus gamma is a number that is very big, right? So in fact, there are already statistically near optimal algorithm that is proved by Cedarford et al. At 2018. They show that they're using model-free algorithm achieving this information theoretical lower bound. However, the algorithm is, of course, model-free, and it's very complicated. It's based on very complicated variance reduction method. Okay. So the question to ask is that can model-based also be optimal as well? Note that the model size of the MDP is proportional to S squared instead of S. Okay, that's the subtlety. So the model-free algorithm based on value, the value function only has a has a complexity proportional to S and A. All right. So talking about the model-based algorithm, we can see the most basic one, that is the empirical risk minimization type algorithm. So that is like this. First, we collect a bunch of samples from each state action pair, and then we use this set of samples to construct an empirical model, and which is also very easy, right? So you just count how many transitions from one state action pair to another state and divide by the total number of counts there. That gives an empirical estimator for the probability. And then then we'll apply any like plugin solver on this empirical model. Then we get let's say a policy from this empirical model. So, but talking about plugin solver, I mean any kind of, let's say, dynamic programming method like value iteration, policy iteration, or you can use other advanced method like the ones proposed in C4 et al. Okay. The question to ask is that, is this algorithm very good? So in terms of statistic sample complexity. Okay. And so this algorithm, because of its simplicity, has been studied a long time ago. For instance, by the original Azaro paper, they show that if the agent collects sufficient many samples, so the number of samples is proportional to 1 minus gamma to the minus 5, which is a big number, by the way. So the algorithm is guaranteed to output a good policy. Okay. However, there is a huge gap between this and this information theoretical lower bound, right? So the upper bound is -5 and the lower bound is -3. All right, so our paper gives the result saying that this simple algorithm is statistically optimal, meaning that we show a sufficient condition that the algorithm use this number of samples can be guaranteed to output a good policy with high probability. Okay. So to get this result, we in fact reduce the whole thing, the error of the policy, into this simple equation. Okay, so the error of the policy into this simple equation. So this policy pi is coming from the plugin solver of the optimal policy, or the optimal policy of this empirical model. Okay. So this equation, as you can see, it's the inner product between the value function. Okay, so this p hat is the empirical model, empirical probability that we constructed using the samples. So it's the inner product with the empirical probability with the v hat, which is the optimal value function of the empirical model. Okay. So the difference between this and this, the same vector inner product with the true probability transition. Yeah. So as you can see, this quality is in reminiscent of this a lot of concentration inequality, like Hauff-Ding inequality or Bernstein inequality. In particular, this p hat, this p inner product with a vector v, is the expectation of a random sample, a coordinate from this v, right, from this v hat, based on this particular distribution, right? And then we are using the empirical probability to compute an estimate for this. So one naive idea to think about to bound this error is to apply concentration inequalities like Bernstein or Hauff-Ding inequality, right? So, however, the subtlety is that this v hat, as you can see, its empirical optimal value function is computed using the samples of this p hat. In that way, these two quantities are highly dependent with each other, right? So you cannot apply Hauff-Ding inequality or Bernstein inequality because you don't have independence. Okay. So the primary goal of the paper is to decouple this inner product. Basically, we want to, let's say, build another thing such that the p hat and the other thing are independent, and then we can use this to apply concentration inequalities. Right. So what's the most natural idea? The most natural idea is, of course, build a net, right? So an epsilon net. Let's say epsilon net is a set of vectors that covers this value function, meaning that there exists a vector in this net that is very close to this value function, right? So then we can apply a union bound using concentration inequality of every vector in the net. After that, we can establish an arrow bound, right? However, a direct union bound will be we first construct the most naive epsilon net over this value function. That will be the S-dimensional epsilon net. Note that this value function is an S-dimensional vector, right? So the epsilon net will have size 1 over epsilon to the S many vectors will contain that many vectors. So if you apply a direct union bound, you're gonna get a bound that is S factor worse, right? So in fact, in the paper, we showed that because this direct union bond is using a deterministic epsilon net, right? So the size is very big, right? So in our paper, we are constructing a randomized epsilon net that is actually very small. In fact, it's a one-dimensional epsilon cover to cover this value vector, and then based on this, we can apply union bond and lose only a small factor in terms of sample complexity. And in particular, this net is going to be independent with the probability vector. Okay. So in more detail, what is our construction for the net is like this. So if we look at closely at this probability transition, right? So in order to obtain this value function, we basically we basically solve the empirical MDP to obtain this, right? So in order to obtain like independence with this probability transition, so we can replace it with another deterministic transition. For instance, in this empirical Markov decision process, we replace the transition at this particular state S, okay, every particular state S, with the absorbing state. In that way, the transition is always transitioning back to itself. So the transition is deterministic. So the transition is, of course, independent with the original probability transition, right? So in this way, we construct a new thing that is independent with this original probability transition. Of course, you solve this new Markov decision process, you can get a vector. So to obtain that covers this value function, we can adjust the reward function of this arc of this transition. Okay. So in fact, you can show that you can pick a good value U. It's a good value reward applying here. You can obtain exactly the same value as the original one. And so in that way, you can adjust only a single number, right? Only a single number in order to obtain a whole vector. So in that way, we can construct a set that covers this original value function, and then this is only dependent on a single parameter u, that is a one-dimensional net, in other words. Okay. So as you can see, in this analysis, we are basically leave one state out. So it's in reminiscent to this leave one out analysis in statistics. So as to mention the properties, right? So this new net is of course independent with the probability transition that satisfy our requirement, and the secondly, it is a cover of this value function. Next, you can just discretize this set to obtain an epsilon net. We can then apply a union bond, right? Because of this, we are establishing a sample upper bound of this simple plug-in model-based approach, saying that as long as the agent collects, let's say, a number of samples proportional to 1 over 1 minus gamma to the 3, and linearly proportional to the number of states and actions, and then 1 over epsilon squared, then this algorithm is guaranteed to output a very good, let's say, epsilon optimal policy with high probability. So in particular, this theorem applies to any plugin solver. For instance, you can apply a policy iteration, value iteration. So there's no requirement on this solver of the empirical Markov decision process. Also, even this, let's say, the solver is approximate, saying that you have some amount of optimization error. The optimization error does not affect the final accuracy by much. It only affected by 1 over 1 minus gamma factor. Okay. So there's subtle issues on the epsilon though. So as you can see in the theorem, so we require epsilon to be in between 0 and the square root 1 over 1 minus gamma. So in fact, the value can be as big as 1 over 1 minus gamma. So this epsilon is not about the full range though. So, but it is actually improving other papers. For instance, previous papers only the epsilon is only in between 0 and 1. So the full range is 0 to 1 over 1 minus gamma. So this was an open question. However, it has been solved recently by a paper by Li et al. Okay. So in conclusion, we show that model-based empirical risk minimization can achieve statistical near optimality for learning the policy of a Markov decision process. In particular, the model we constructed is of size S times A, that is very small compared to the full model size. Okay, so we're establishing a new decoupling technique to analyze this Markov decision process in order to establish our bond. So as an open question that is, can we extend this analysis to the online setting? Thanks.